Нет, экран. Я, правда, участников не вижу. А, нет, теперь вижу.
Все хорошо.
Угу.
А я включился, смотрела, у меня как-то чужие.
Да. Садись со мной, это мне самое страшное. Так, а тут у нас... То есть я могу управлять...
Так, а вы выключите пока звук.
Так, все наши докладчики здесь. Так, Калинин Ростислав здесь. Угу. Уважаемые коллеги, приветствую всех на заседании сессии «Люминесценция». Слышно ли меня?
Dear colleagues, I welcome you at the session devoted to luminescence.
Продолжается работа нашей сессии.
We continue our work at the session.
И я хотела бы проинформировать уважаемых коллег, что для обсуждения докладов как устных, так и постерных, так называемые кулуары, в рамках нашего конгресса предусмотрен форум.
Well, I want to inform the colleagues that for the discussions of both oral and poster reports, we have especially devoted for this purpose forum.
Там размещены все доклады, можно задавать вопросы.
All the reports are presented there, and you can ask your questions in this forum.
Спасибо. Сегодня мне помогает для организации работы сессии Ростислав Калинин. Спасибо ему.
Today my assistant is Rostislav Kalinin. Thanks to him.
И, пожалуй, я предоставлю слово первому докладчику.
And I want to give a word to the first reporter.
Это приглашенный доклад Елена Бочарникова, Томский государственный университет, выступит с докладом Luminescence Analysis of Photo Degradation of Crystal Violet Exposed to Pulsed Power Beams.
This is an invited speaker from the National Research Tomsk State University, Елена Бочарникова.
Елена, пожалуйста, вам слово. Мгм. Стрелочками можно переключать слайд. Елена. Так, некоторые тут заминки технические. Минутку ждем.
Sorry for some technical problems. Let's wait for a minute.
Не тот, не те слайды. Нет, нет.
Я, в принципе, презентацию.
Елена, это ваш доклад, да, вот сейчас?
Я вообще не вижу, у меня черный экран, я не вижу презентации вообще.
Угу. Ну, я вижу презентацию, но вот это, по-моему, последний слайд вашего доклада. Ростислав, какие там у нас проблемы? Елена, вроде бы вот сейчас все наладилось. Вы видите свою презентацию? Елена. Елена, разобрались, как работать?
Я не могу
Готовы?
вывести на экран, ну, вроде бы да. Ну, первый слайд,
Вот
правильно?
сейчас презентация на экране, и вы включаете стрелочками слайды. Вот опять исчезла презентация. Так, ну, так, сейчас все видим. У вас все в порядке, Елена?
Вот, все, сейчас я тоже вижу презентацию, могу начинать.
Угу. Пожалуйста.
Good day, dear.
Так, а я не вижу теперь презентацию. Угу.
Продолжаю. Good day. My name is Elena Batyeva. I'm a postgraduate student of the Faculty of Physics at Tomsk State University. The staining dye crystal violet is used for human medical cell diagnostic and serves the purpose of the bacteriological investigation of sample materials of human origin. The structural formula of crystal violet is shown in the figure on this slide. In the order to establish the best orientation condition for the continuous photoreactor, discontinuous photodegradation studies were carried out for crystal violet with X-lamp in water. In order to establish the mechanism and kinetic on the photocomposition, the advanced oxidation processes were provided. The study was carried out both in the absence and the presence of hydrogen peroxide dose until dye concentration effects were examined. Effluents contain high levels of environmental contaminants, strong color, and the same. The aim of the work is to study the spectral and luminescence properties of photoactivated crystal violet when exposed to ultraviolet X lamps in solution. Experimental studies of the spectral luminescence characteristics were carried out on a CM2203 spectropolarimeter at room temperature. The absorption and fluorescence spectra of crystal violet in hexane, water, and ethanol were recorded. The next stage of this work, the irradiation of aqueous solution of crystal violet in a stationary photoreactor. At the stage of the work were performed an experimental in which irradiation of aqueous solution of crystal violet was carried out in a stationary photoreactor at room temperature. Spectral luminescence properties were obtained on CM2203 spectropolarimeter. Krypton fluorine and xenon bromine XLAMPs were used as source of ultraviolet radiation. The control exposure time, you can see this slide. The ratio of hydrogen peroxide by crystal violet in the aqueous solution was as following this slide. Ultraviolet irradiation can destroy organic contaminants, including crystal violet, source direct and indirect photolysis. An analysis of the rate constants of the crystal violet disease in water under the action of krypton fluorine and xenon bromine radiation to XLAMPs. The addition of hydrogen peroxide reduced crystal violet in solutions at the conversion in 93%. The HPLS date of the radiated solutions for 60 minutes showed that in addition to crystal violet, the products of its phototransformation are also contained in the solution. You can see the results of this work done on the slide. That's all. Thanks for attention.
There is a question in the chat. How was the absorbed energy controlled?
Can I answer your question in Russian language?
Yes, yes.
Да? Ну, смотрите, мы, получается, что снимали растворы до поглощения энергии и после, то есть мы отслеживали это.
We checked the solution before energy absorption and after energy absorption.
Длина волны излучения используемых источников у криптон-хлора это 222 нанометра, а у ксенон-брома 283 нанометра.
The wavelength for krypton chlorine was 222 nanometers and xenon bromine 283.
Екатерина, вопрос Александра в чате.
Что такое длина волны? Длина волны – это расстояние между двумя ближайшими точками в пространстве, в которых происходит колебание.
Нет, здесь не определение, здесь...
Вот, просто что именно вы хотите услышать тогда?
Нет, вы ответили на вопрос, спасибо. Вопрос от Александра Сюрдо. What radiation power of XLAMPs do you use in your experiments?
Я сейчас не отвечу на этот вопрос.
I cannot answer this question right now.
Коллеги, еще вопросы, пожалуйста.
Colleagues, sir, any other questions?
Скажите, в ваших растворах что является центром свечения?
What is the glow center in your solutions?
Ну, у нас само вещество является флуоресцирующей меткой, оно достаточно хорошо светит.
То есть это, собственная люминесценция.
Да.
То есть
Да.
никаких активаторов туда не добавляется.
It is the intrinsic luminescence because the substance that we use itself is fluorescent. We do not use any activators.
Понятно, спасибо, Елена. Уважаемые коллеги, еще вопросы, пожалуйста.
Any other questions, colleagues?
Вопросов вроде бы больше нет. Спасибо, Елена,
It seems
за
we have no
интересный
more questions.
доклад.
Elena, thank you for this report.
Слово для следующего доклада предоставляется Александру Тюрину.
Now a word is given to Alexander Turin
Из Иркутского института лазерной физики. Вы на связи?
from the Irkutsk branch of the Institute of Laser Physics. Are you with us?
Do you hear me? Someone hear me?
Yeah, we can hear you.
Okay. Okay, I can start, yes?
Yes, yes.
Okay, good afternoon, ladies and gentlemen, or good morning for someone. My name is Turin Alexander. I'm a scientific researcher from Institute of Laser Physics. Today I'd like to tell you about the glow discharge application for formation of a thin luminescent layer in wide gap crystals. I think this topic will be interesting for you because application of luminescence point defects, namely color centers, are huge in different fields of science and industry. I have divided my presentation into three parts. I will begin with the introduction, where I will try to explain relevance goals and tasks. Then I will tell you about experiments we have made, and in conclusion, I will tell you about our results. My presentation will take about 15 minutes to cover this part. Okay, the first part of the presentation is an introduction. Slide number 2. Yes. Okay, luminescence properties of point defects is insulating material are successfully used for solid-state light sources and lasers and radiation detectors. Interest in radiation optical technologies in which core centers formed in both the value and surface layers of the electric materials are used as working quartal system has grown in recent years. For instance, you can see some examples of reference our work. You can see the also from Italy. One second. From Italy, develop methods and tools for invisible market of goods, documents, and artistic work with encoded luminescent labels based on the lithium fluoride particle center on the special film substrate. You can see a special luminescence label on the transistor here. Another example, a technology for the recording of a microtext in a thin single crystal layer with the use of laser-induced plasma, throughout radiation, focused with a Schwarzschild lens. Was implemented in this work, you can see here. Apart from these examples, scientists tried to find more easy and effective ways of ionism influence on materials. Good example can be work about formation of color center of a thin layer of lithium fluoride crystal under vacuum throughout radiation from a barrier discharge. The study of color centers and mechanisms of their formation under different physical impacts and the development of various applications associated with them remain a relevant problem. So in our work, we continue to investigate application different discharge for the color centers formation in insulating material, which we started in this article. You can see here on the bottom of slide. Today we will consider the glow discharge. Okay, slide number 3. 1 second. Slide number 3. The purpose and task. The purpose of the work was to investigate the glow discharge application for formation of thin luminescent layer in wide gap crystals. The task was to study the axial intensity distribution of the vacuum throughout radiation of glow discharge in air, depending on the voltage and pressure. To identify glow discharge region in which the formation of defects is most efficient, to determine the types of color centers and their spectral and kinetic characteristics. Next slide, slide number 4. What is glow discharge? The glow discharge is a kind of plasma which is created by inserting 2 electrodes in a cell filled with gas at low pressure. You can see a typical structure of glow discharge here, and one of the image our experiments in the bottom of the slide of glow discharge is here. There are 2 most important types of collision, excitation and ionization of gas atoms. The excitation collisions and subsequent de-excitation to lower levels by radiative decay are responsible for the characteristic glow in glow discharge. For example, the negative glow contains the lines at 391 nanometers, 57 nanometers, 427 and 70 nanometers. The Faraday dark space contains bright lines at 399 nanometers, 26 nanometers, and the positive column contains bright lines at 357, 80 nanometer, 99, and of course the brightest lines what we see here at 662 nanometers. Okay, the next slide, slide number 5. In order to create a color center in the crystals, I need the interband ionization. There are only three processes can be do it: electrons, ions, and photons. In our previous work, yes, in this article we have shown the luminescence layer formed by a photon-induced mechanism, namely by vacuum throughout radiation. But what regions of glow discharge emit vacuum throughout radiation? So it's not easy question because the radiation of discharge depends on 5 variables. One of them potential difference, distance between the electrodes, pressure, type of gas, and of course electrode material. So we need to obtain the axial vacuum throughout radiation intensity distribution of glow discharge. But it's not easy too, because measurement is difficult in vacuum throughout range. So how do we plan? Sorry, next slide, slide number 6. So how we? 1 second. So how do we plan to obtain vacuum throughout radiation distribution? In order to answer the question, we carry out experiments with synthesized calcium sulfate with manganese, terminal sensitive to radiation in spectral region shorter than 130 nanometer. And some details about this terminal you can see in this frame. And we synthesized this terminal form, and on the right slide you can see glow curves. This terminal flow after radiation by glow discharge at different voltage, and in order to check that our terminal flow it's not sensitive to wavelengths at, for example, to 200 nanometer, we carry out it too, and we see it's not glow curves. Okay, Next slide, slide number 7. To obtain the axial vacuum throughout radiation intensity distribution, a special copper plate coated with this terminal layer was placed a special diaphragm cell, you can see here. The cell was installed on the internal of the discharge. You can see a block diagram experimental step here. After irradiation, the samples was heated and its terminescence curve was obtained by scheme. You can see here on the slide. Then the terminal was placed in another area of loss discharge. One of them was here, then another was placed here, and etc. This procedure continues until we get all the terminescence curves from each area of discharge. It's worth noting that intensity of vacuum throughout radiation of glow discharge highly depends on voltage between electrodes and pressure in chamber. So we did experiments depends on these parameters. Next slide, slide number 8. On this slide you can see axial vacuum throughout radiation distribution of glow discharge depends on voltage and pressure. The intensity distribution of the detected thermopeaks reflects the vacuum throughout radiation intensity distribution along a discharge. From figure on the slide, it can be concluded the glow discharge in the air emits photons in the vacuum throughout region practically through in the lens with different intensities. The most intense region of vacuum throughout radiation are the near electrode regions, I mean here and here, of the discharge here. So what need to say more? On the slide is also shown the positive column. It starts here. The positive column of the glow discharge also have intensive vacuum throughout radiation. You can see here. These peaks at range at 10 to 25 millimeter are due to stratification process of the positive column. The axial voltage gradient at the beginning of the first stratum here is higher, which leads to ionization and excitation of neutral molecules. So the gas discharge region in which vacuum throughout radiation is generated as the anode glow film is here. Strata of the positive column here, and the near cathode discharge region is here. Okay, next slide, slide number 9. So what happens if we place a lithium fluoride crystals in the glow discharge? But first of all, let's take some experimental setup details. The experimental setup is composed of vacuum chamber, inside which you can see here, inside which a glass tube, scheme is here, with a diameter of 2 centimeters. In the chamber, glow discharge was formed in air at pressure of 50 Pascal and at 1.25 kilowatt. A glow discharge at such pressure is characterized by presence of major extensive region, namely the positive column, you can see here, and the Faraday dark space here. Lithium fluoride crystal were placed in this region. One of them was placed in the positive column, you can see here. Then it was irradiated by a glow discharge. Then it was heated and we obtained the terminance curve. Another lithium fluoride crystal were placed here in the Faraday dark space, and we also obtain the terminescence curve. So let's go to the next slide, slide number 10. 1 second. On the slide, you can see the luminescence spectra and kinetics of irradiated lithium fluoride crystals obtained by using microtime laser confocal scanning luminescence microscope equipped with ocean optics spectrometer. Luminescence measurements results show that the two major types of color centers were created in lithium fluoride crystals, namely F3+, and F2 sensor with luminescence band at 540 nanometer and 680 nanometer. And decay time constants of 6.8 nanosecond and 17.8 nanosecond. The high concentration of luminescent defect correspond to the size of the crystal face to the electrodes, curves 1 and 2. You can see it's here, it's a red gradient in here. And the smallest defect concentration correspond to a low intensity of vacuum throughout radiation in the dark Faraday space. So next slide, slide number 11. So after obtained result, we can conclude that the color centers formation is not provided electron mechanism, electron bombardment. It's provided by photon mechanism. Electron hole pairs and excitons formed about the absorption of radiation in this line form a Neuronic-Franklin defect, which are initial product for the creation of aggregate color centers. So let's go to conclusion. So it was obtained the axial vacuum throughout radiation intensity distribution of glow discharge. The vacuum throughout radiation intensity distribution has maximum values in the near electrode region of the discharge in the pressure range of 50 to 530 Pascal and voltage of 1 to 3 kilovolts. The stratified positive column of low discharge is also a region of intense vacuum throughout radiation at high voltage. But it has been established that basically two types of color centers are formed on the surface layers on crystal, F2 and 3 color centers. After what I say, I just can say that the glow discharge can be successfully used for form thin luminescent layer on the surface on transparent insulators for various scientific and practical application. So thank you very much for your attention. If you have some question, I'm glad to hear it.
Спасибо, Александр, за интересный доклад. Уважаемые коллеги, пожалуйста, вопросы.
Thank you, Alexander, for an interesting report. Dear colleagues, your questions, please.
Александр, вот литий фтор вы используете чистый кристалл, да?
Yes. Pure little fluoride crystal.
А какие-то сведения о дефектности, содержащейся в этом кристалле, у вас есть? Ну, изначально?
Do you have any information about the defects that are being present in these crystals initially?
No, it's not provided. Some experiments with these crystals. My scientific advisor just said this is a pure crystal, and I approved it. And I don't check it.
Нужен на русский перевод.
Спасибо. Нет, спасибо.
Okay.
Вопрос в чате, Александр. На какой глубине можно получать тонкие слои?
At what length can you obtain thin layers?
So if we talk about vacuum throughout radiation, the depth of its propagation, it's about 10 and more nanometers.
10 and more.
10 nanometers and more, of course. But our equipment, it's not provide to check the thickness of luminescence layer, because it's just optical limitation. We can do it.
Еще вопросы, коллеги? Доклад на самом деле очень интересный, насыщенный, и я думаю, вопросы можно Александру задать на форуме, если они у вас возникли.
Yes, of course.
The report is very informative, and I believe that we expect some questions in the forum.
Спасибо, Александр.
Thank you. Okay.
следующему докладчику. Слово для доклада предоставляется Артему Мережникову, Уральский федеральный университет.
The next report is presented by Artem Merezhnikov, Ural Federal University.
Артем, вы слышите нас? Артем, откликнитесь. Угу. Нет, не слышим мы вас пока что. Уважаемый модератор, Артем Мережников у нас вышел в эфир?
Hello? Do you hear me?
Yes, yes.
Oh, thank you.
Пожалуйста, Артем, вам слово.
Dear colleagues, today I'm going to present you a theoretical study of thermoluminescence, those effects in cluster model with deep hole traps. Thermoluminescence is widely used in dosimetry and study of defect properties in wide gap insulators, study of formation of complex tail dose dependence, such as nonlinear dose dependence, is of great interest. It is known that the competition processes associated with the presence of deep hole traps in phosphorus can cause nonlinearity of tail dose dependence. Also, non-monotonic tail dose dependence is observed in a number of materials, for example, in lithium fluoride. Usually, presence of non-monotonic tail dose dependency is explained by radiation damage of trap in centers. At the same time, competition processes which involve deep hole traps was used to explain non-monotonic tail dose dependence. It is known that models with cluster defects are used for describing tail kinetics in polycrystalline and nanostructured phosphorus, as well as phosphorus irradiated with high doses. For example, Mondowski was the pioneer who applied such models to describe tail kinetics in polycrystalline phosphorus. In such models, transitions between different localized levels in the cluster are taken into account along with the delocalized transitions. It is known that presence of localized transitions can lead to anomalous heating rate effect, which was observed in several materials, for example, in yttrium phosphate doped by cerium and samarium. Models with deep hole traps in the cluster have not been investigated earlier. We expect that presence of deep hole traps in cluster model can lead to new features of tail dose dependence. So our aim of the research was to analyze tail dose dependencies in cluster model with deep hole traps and study influence of localized transitions on features of tail dose dependencies. Let us go through the plan of the presentation. First, I will tell you about the cluster model. Then I will describe the simulation process, calculation method, and algorithm. Further, I will discuss some analytical approaches for the model. And finally, several cases will be considered as examples. In the figure, you can see a scheme of the charge carriers transitions between different energy levels. The main feature of the model is the presence of so-called localized transitions between energy levels contained in same cluster transitions A, B, and C. The presented model belongs to the class of tail kinetic models proposed for the first time by Mondowski and developed by other authors, for example, Pagonis and Horowitz. Such models consider the main tail active trap as two energy levels, ground and excited states. Also, possibility of electron transitions directly from excited level to luminescence center is assumed, transition B. The main difference of the introduced model is the presence of deep hole traps along with the luminescence center inside cluster and corresponding transitions. Each cluster contains the same number of electron tail active traps N, luminescence center H, and deep hole traps M. We assume that number of electron traps is equal to sum of both luminescence center and deep hole traps. The restriction is based on assumption that such cluster is more stable due to Coulomb attraction between defects of different charge state. On the slide, upper figure shows possible transitions on irradiation and relaxation stages, except for transition X, which is possible during irradiation stage only. At irradiation stage, electron pairs are formed, then conduction band electrons and valence band holes are captured by corresponding centers. Also, electrons can recombine with holes in hole trapping centers. At the relaxation stage, electron-hole pairs formation is absent, remaining delocalized electrons and holes continue being captured by corresponding trapping centers. At the heating stage, thermal stimulation probabilities increase due to temperature growth. Electrons in the ground state can move to the excited state, NE, transition PN, and reach the conduction band, transition PNE. During this stage, electrons also can recombine with holes in hole centers inside same cluster. Conduction band electrons can be retrapped by cluster, recombine non-radiatively with holes in deep hole traps, and recombine with holes in luminescence centers radiatively. The number of radiative recombination per time unit stands for thermoluminescence intensity. We used Monte Carlo method for simulation charge carrier transfer between different energy levels. Each stage is characterized by a set of possible transitions and ending condition. At any stage, iterations are executed until the condition is reached. On each iteration, random time is generated for every possible transition. Among the obtained times, the shortest one stands for occurred transitions. According to the occurred one, occupancies of levels are recalculated. The exponential probability distribution was used for random times generation, and the program was developed in C++. Here you can see the probability equation for each transition. Generally, each probability coefficient is defined by levels occupancies and some coefficients which are determined by physical properties of defects. One should determine upper limit of the exponential integral for thermosimulation transitions. Since it can be expressed with elementary functions, an estimation of the integral was used. Here you can see the table of default parameters that was used during simulation. The main feature of the values is that activation energy ENE is greater than EN, and the probability coefficient of hole capture to hole trap is much greater than 1 for luminescence center. Let us consider some analytical estimations before simulation results are shown. We'll describe limit case when activation energy ENE is much larger than activation energy N and heating rate is small. In that case, probability of transition PNE is very small compared to probability of transition PN. Also, we consider a case with relatively small values of cluster trapping coefficient alpha. We'll divide the whole temperature region during heating in two subregions, low temperature region and high temperature region. It is expected that under such condition, in low temperature region, only localized transitions occur since no electrons will reach conduction band. Conversely, in high temperature region, only delocalized transitions occur since cluster which contain only electrons on only holes will be left. We are interested in the number of left electrons and holes after low temperature region. Let us consider the simplest case, no deep hole traps in cluster. According to previous assumptions, we can estimate the number of delocalized radiative recombinations during heating stage. Let us estimate the number of electrons which will participate in delocalized recombination. Obviously, each cluster which contains no electrons will not invest such electrons. Each cluster which contains one electron and no hole invest one electron since there is no hole with which electron can recombine inside cluster. Cluster which contain one electron and one hole will not invest any electron since they will recombine with holes via localized transition B. Therefore, the number of left electrons is the number of cluster which contain one electrons and no holes. In the figure, you can see that thermoluminescence curve, number of free electrons and number of occupied luminescence center after low temperature region fit with each other. It can be seen from previous consideration that competition between thermal stimulation transition PNE from excited state to the conduction band and localized transition recombination D during heating cause non-monotony of tail dose response. Let us describe more general case when activation energy ENE is still greater than trap activation energy, but not as much as in previous case. In the figure, you can see tail curves calculated with different heating rate. Shifting of tail curves toward high temperature regions with increasing heating rate is known effect. Since at high temperature, probability of electron leaving cluster is higher, more electrons reach conduction band and radiatively recombine with holes in luminescence centers. This effect is called in literature as anomalous heating rate effect. The effect is also noticeable in figure with tail dose dependencies. Also, in this case, at low heating rate, tail dose dependency is non-monotonic. It can be explained by approaching of condition to extreme case when all localized transitions executed before the localized ones. In the second figure, tail output doesn't fit with the number of left electrons and occupied luminescence center after low temperature region completely. But it can be seen that derivative of the tail dose dependence changes sign near intersection of curves with state of cluster characterized by one hole and one electron and state with one hole only. In that intersection point, number of completely occupied cluster becomes greater than of cluster with electrons holes only. Let us consider the case with deep hole traps in clusters. Presence of deep hole traps make analytical consideration of tail output on heating stage slightly more complex. Influence of localized competition between deep hole traps and luminescence center on tail dose dependence is expected. According to our previous analytical estimations, let us show the expression for left electrons. As in previous case, we take into account strong influence of localized recombinations. Thus, each cluster which contains electrons and holes invests less electrons than cluster which contains electrons only. For example, clusters with 2 electrons, one occupied luminescence center and one occupied deep trap, invest no electrons since they will recombine with hole during heating in low temperature region. The expression for left electrons is given below. Similarly, we will consider expression for the number of occupied luminescence center at the end of low temperature region. The main difference in the localized competition between hole trapping centers in comparison with previous case, it is represented in case with cluster which contain both luminescence centers and deep trap occupied by hole and one occupied electron trap. In that case, we can estimate the number of occupied luminescence center after low temperature region using values of corresponding probabilities coefficients B and C. Here a similar expression for deep hole traps are shown. The figure shows those dependencies for occupied trapping centers after low temperature region. Tail curve has several regions with different nonlinearity indexes: linear, superlinear, sublinear, and non-monotonic. It can be seen that tail output fits with the number of occupied luminescence centers after low temperature regions, since they stand for the number of radiative recombinations during heating. Insignificant difference between the dependencies can be explained by non-fulfillment of mentioned conditions and random deviations. Let us describe the case when activation energy of cluster is equal to 0.85 electron volts. Tail output still increases with increasing heating rate. As probability of transition B is equal to 0, tail output is maximized and tail dose dependence become monotonic. In case when B is more than 0 and probability of transitions C is equal to 0, tail output is the lowest, since localized competition between luminescence center and hole trap in the same cluster vanishes and more holes in luminescence center recombine with electrons non-radiatively. The non-monotony of dependencies is hardly noticeable, but presence of regions with different non-linearity index remains. The figure shows influence of activation energy of the cluster value on the non-monotony. Tail output decreases with increasing activation energy. As activation energy increases, model conditions approach extreme case when localized transitions occur only in low temperature region. The conclusions. Tail dose dependence in cluster system with deep hole traps consist of several regions with different nonlinearity index and has non-monotonic region in some cases. Localized transitions on one hand can lead to non-monotonic dose dependence, on the other hand to the formation of temperature-dependent characteristics of dose dependence and tail curves. The presence of deep hole traps leads to temperature-dependent superlinearity of tail dose dependence. The localized competition between hole traps and luminescence centers and energy distance from excited state of the main trap to the conduction band influence on degree of non-monotony of tail dose dependence. This work was financially supported by Russian Science Foundation project. Thank you for your attention, and I'm ready to ask your questions, to answer your questions.
Спасибо, Артем. Уважаемые коллеги, вопросы.
If you have any questions, you ask the presenter. We have a question in the chat, as far as you can
Вопрос
see.
в чате, Артем.
Okay, let me show the table. As you can see, the number of clusters is quite small. It is only hundreds of thousands clusters. This number is small due to some performance issues, because if you will use very large numbers, the time of the calculation will be very big. So I used such number. I can estimate that such number can be contained in maybe cubic micrometer or less, so you can estimate the concentration of such clusters and concentrations of such defects. It is around 10 power 12 or 15 defects per cubic centimeter. And so cluster size is around micrometer or less.
Thank you for your answer. Вопрос в чате. Could you please explain how you linked this simulation code MCNP and C++?
Could you please explain what is MCNP?
Уважаемый Самиру,
Samira, could you please explain what MCNP is? The presenter doesn't understand. What is MCNP?
I guess maybe I can understand the question. I haven't linked anything. All the code was written in C++, all the project, so I haven't used some external libraries or modules or other programs.
Самиру, вы удовлетворены ответом?
Samira, do you like the answer?
Коллеги, еще вопросы, пожалуйста.
Colleagues, you are welcome with questions.
Вопросов пока нет. Думаю, вопросы еще созреют. Артем, спасибо за такой серьезный доклад. Очень радостно видеть, что молодые ученые выступают на таком уровне.
Artem, thank you for your very informative and complicated topic and report, and it is a great pleasure to see that young scientists can present their research in our Congress. Thank you very much.
Спасибо. Уважаемые коллеги, переходим к докладу, который у нас стоит в программе 5 по счету. У наших коллег из Чуньцина возникли... Может быть, к концу заседания они решатся, и тогда мы послушаем доклад. Но сейчас пока слово предоставляется Дамиру Валиеву, представителю Томского политехнического университета.
Dear colleagues, we have changes in our program because our Chinese are having some technical problems now, and we will present their report later. And now we invite Damir Valiyev. This is our colleague from Tomsk Polytechnic University.
Okay, good day everyone. Damir Valiyev asked me to speak with him presentation, and I can start. Okay. Today, my name is Anne, and I am a student at Tomsk Polytechnic University, and today I want to discuss with you on topic effect of ultrasonic treatment on the luminescence properties of conventionally sintered yak with cerium ceramics, and about our motivation. First of all, one of the latest directions in the field of radiation conversion technology for the white LEDs manufacturing is luminescence ceramics, and luminescence ceramics occupies an intermediate position between crystalline materials and glasses. It combines the best properties of crystals, high mechanical and thermal strength, and glasses, the possibility of pressing and forming elements of particularly different geometry. And luminescence ceramics can be close and in some cases even exceed the characteristics of the laser scintillation crystal analogs according to the optical and luminescent characteristics of ceramics. This type of materials can be applied in many different fields, such as scintillation, lasers activating media, and LEDs, and other fields. Okay, as usual, yak with cerium ceramics could be prepared by traditional pressing methods, followed by sintering in air atmosphere or in vacuum and other methods. However, a significant problem of traditional methods is the preservation of the required fast composition, structure, and purity of the material during the pressing process, which cannot fully ensured by traditional methods of power compaction. In this regard, we use in this work methods with ultrasound pressing, and this method includes in particular ultrasound and collector pressing followed by sintering process, and the distribution of pressure and density over the pressing volume becomes uniform due to the reduction of near wall friction when pressing process under treatment using ultrasound. Okay, and our goals of this work, we need to synthesis and do complex study, spectroscopic study of the luminescent ceramics of our samples, and finally we again developed of light source model. What about I say in previous presentation. Experimental technicals you can see on this slide, and ceramics preparation process. Preparation process is the same which we used in previous presentation, but in this work when we use pressing, we use ultrasound too, and we obtained what we obtained we can see on the next slide. the power of the ultrasound waves of the master generation was 800 watts. So about results. First of all, X-rays phase analysis confirmed that ceramic samples have stoichiometric of yttrium aluminum garnet with cubic structure, and we can see that values of grain diameter on the left pictures increased from 0 to 5 micrometers and to 35 micrometers. And the sintering ceramics have a large number of pores, and the grain size remain at the level of several micrometers, corresponding to the average particle size of the original powder. And so the consolidation of the sintered material is very intensive, accompanied by a decrease in the number of pores, and grain growth at the temperature of 1650 degrees. And the comparison process of the sintered yak with cerium ceramics slowed down dramatically at the temperature of 1700 degrees. And this is signified grain growth, leading to the transmission of interpolated residual pores into the grain volume. So luminescence spectra in the spectral region of 400, 800 nanometers, yak with cerium ceramic sintering without and using treatment by ultrasound were excited by 447 nanometers LED chip. There are emission bands in the ultraviolet and in the visible spectral region of yak ceramics at different sintering temperature. So the luminous efficiency of excitation conversion into the visible light is main characteristics of the phosphorus ceramics and necessary for its use in the light source. The estimation was made by measuring of energetical spectra. It presented results. You could see the good correlation between luminous efficiency and reflectance of yak ceramics. And on the right picture, you can see temperature resistance of samples with ultrasound and without ultrasound. And you can see maybe not big value, but it's between около 10%, and it's maybe important when we use high power light sources. And according to our estimates, the luminous efficiency of the obtained ceramics directly connected with data reflection, as was demonstrated previously with a decrease in the reflection of the excitant light increases the luminous efficiency, which is quite logical. At the same time, the luminous efficiency in the USA remains unclear from the presented results, and the decreases in luminous efficiency at 1700 degrees is also not clear. And we use mean theory to understand and to explain this phenomena, scattering calculation. Okay, and again, at right picture, you can see that scattering of our sample without ultrasound is bigger than with ultrasound. And again, how we demonstrate in previous presentation, we use white emitter design and its concept to analyze our samples in future. And the summary, luminescent ceramics based on yttrium garnet were obtained by axial pressing using ultrasound, and we did study of characteristics of these samples, and we have a layout designed of ceramics emitter, and I think it's all. I not read full summary. Okay, it's all. I will be glad to answer your questions. If I can, I answer on Russian. Воздействие ультразвука может создавать какие-то дефекты в кристаллах керамики, либо влияние наблюдается только на структуру. То есть изначально влияние наблюдается на структуру. При воздействии ультразвука мы получаем более интеркристаллическую структуру, как видно на изображении.
So initially the influence is only on the structure, as far as you can see on the slide.
Без воздействия ультразвука на изображении видно более слипшиеся участки, таким рабочим крестьянским языком, если объяснять. А при воздействии ультразвука, то есть у нас более кристаллическая структура.
Under the influence of ultrasound, we have a more crystalline structure, and without it, we have the groups of particles.
Yes. И в результате мы можем предположить, что из-за этого мы получаем, например, эффективность с воздействием ультразвука больше, именно конкретно при температуре 1650 градусов.
And we can state that with the influence of ultrasound, the influence is bigger, and the temperature, and at about the temperature 1600.
Но нужно еще изучать, вызывает ли это дефекты в кристаллах. Это хороший вопрос.
But we need to study if it provokes some defects in the crystals. It is a very good question. Thank you.
Okay, it's all, or I wait the question.
What is the power of ultrasound influence?
800 watts, 800 ватт.
Уважаемые коллеги, спасибо за ответы. Уважаемые коллеги, есть ли еще вопросы?
Dear colleagues, do you have any other questions?
Вопросов нет. Вопросы, пожалуйста, на форуме задаем докладчикам также.
Please use the forum to ask your questions.
Спасибо, Анна.
Thank you, Anna,
за интересный доклад.
for your very interesting.
Так, уважаемые коллеги, продолжаем работу нашей сессии.
Dear colleagues, we continue our session.
И слово для доклада предоставляется Елене Трофимовой,
And I would like to give a word to Elena Trofimova,
представителю Уральского федерального университета.
she is the representative of the Ural Federal University.
Елена, здравствуйте.
Да, здравствуйте.
Вот теперь слышно.
Can you hear me? Okay. Let me start. To manage the transfer processes in lithium strontium phosphate between various ions. Here is a short outline of my talk today. I would like to point out that we have limited time, so the introduction part will be very short. And if you have any questions, I would be glad to discuss. The main reason we started these materials is that there is a need for new white light emitting diodes for solid state lighting. And the challenge is that currently used white light emitting diodes do not provide warm white light. And there are different approaches to obtain this white light. I will show just two of them. The first one is to use red phosphor. There are different ways for red phosphors, a lot of them, but one of the examples that are very close to the topic that we discuss is samarium 3+. It was widely studied earlier, and you can see one of the examples. The researchers have obtained the light from this material, which is very close to red light, as you can see from the right side of the picture. Another approach is to use single-phase white phosphors. We don't need another phosphorus to obtain this white light. And one of the examples is dysprosium 3+. It has a spectral lights that combined produce white light, as you can see from the right picture on the slide. It is very convenient because we don't need another materials to obtain this light. Speaking about hosts and matrices, there are a lot of them, and they were widely studied, but currently a lot of attention is attracted by the family ABPO. It is a family of phosphors where A and B stand for a wide variety of ions. In our case, it's lithium strontium phosphate. Actually, there is a very limited number of works in which praseodymium 3+ ion is studied as an activator. But this ion is very interesting because it has a strong absorption of in ultraviolet region, and it exhibits a number of spectral lines, including some lines in the red region, which could also be used in our aims and applications. Here's a very brief introduction part, and now let's move on to experimental part. So the objects were lithium strontium phosphate crystalline powders doped with praseodymium and either dysprosium or samarium ions. All the ions were trivalent. The experimental methods applied were carried out at the University of Tartu, which is in Estonia. We used direct excitation in ultraviolet and vacuum ultraviolet range, as well as cathode rays with time resolution. And now to experimental results. I'm very sorry for such a quick pace, but I have a lot of information to talk about. So if I'm speaking too quick, you can type message in the chat, and I'll try to slow down. So speaking about photoluminescence, we had to use different time gates because praseodymium 3+ is known for its fast interconfigurational transitions. And in order to distinguish this fast emission, we have to use a very short time gate, which is from 0 to 33 nanoseconds. Okay, but we are more interested in slow emission in visible range. And here on the left part, the spectrum for dysprosium codon sample. It has these two characteristic spectral lines, as I have shown earlier, and a number of weaker lines in red and infrared region. This is actually what we have expected, nothing special about this spectra, but it is more interesting to look at samarium codon sample spectra. For example, we have not just prevalent samarium spectral lines, which are also expected in the red region, but also there is some emission of divalent samarium ions, which is more close to infrared region. And also there is emission that can be assigned to divalent samarium 2+, including fast transitions from 5D levels to 4F levels. It is fast. And this is interesting because it proves the assumption that rare earth ions stand on the strontium 2+ side in the crystalline lattice. To understand all the energy processes in this material, we had to use direct excitation. And here we use two types of excitation. The first one is 165 nanometers, which is very close to energy of host absorption. And under this excitation, we can see praseodymium-3+ emission as well as the emission of cold opens. Nothing interesting and nothing special about it, all as we have expected and we have seen in the cathode luminescence spectra, but under direct excitation of praseodymium-3+ straight into its 5D band, which is 225 nanometers. We don't see these emission lines of dysprosium, neither samarium, but in the case of samarium, we can actually see some weak emission in the red region, which is peculiar because it probably indicates some energy transfer processes from praseodymium to samarium. And it is also very important to point out that we can observe some unknown emission, additional emission, which cannot be assigned to the emission of these activators itself. We assume that it is some kind of defect influence, and we have not yet studied this in details because it is clearly out of the scope of the current research. But to understand all we have seen in the previous slides, we have to study excitation spectra of all these lines. And here I would like to point out two things. Firstly, the blue lines on this spectra stand for praseodymium-3+ FF emission at 487 nanometers. In the case of dysprosium, dysprosium also has the emission at exactly the same wavelength. So in this subject, we want to distinguish praseodymium-3+ emission and from dysprosium, and we can see that emission at this line is very weakly excited in the region of direct praseodymium-3+ excitation. The second point is the green lines in the spectra. It was measured for this presumable defect, and it has a band in the region of 300 nanometers, which cannot be assigned to any excitation transitions in these cold-opened ions. And also, you can see that in blue lines, which, as I said earlier, stands for praseodymium FF emission, it also can be excited in this region. And it probably indicates that there is also energy transfer between this presumable defect and activators. In order to verify that, we studied emission spectra under this excitation, and indeed, we can see that this defect emission is intensively excited under this excitation, and there are also emission lines of these activator ions, which proves our assumption. And another interesting thing is that in the right side, emission spectra for samarium doped sample, there are also lines that can be assigned to divalent samarium, which weren't seen under host absorption excitation nor this, praseodymium direct excitation. So it proves that these defect influence should be studied in more details. So speaking about what we wanted to study, energy transfer between activator ions. Again, there is nothing special about dysprosium-3+, except for the line that is overlapping with praseodymium, but it is interesting to consider what happens in the object doped with samarium. If we consider the energy level diagram, we can really see that the energy transfer from Praseodymium to samarium is possible. That means that probably Praseodymium 3+ used in pair with samarium can enhance the emission of the latter. Okay. Again, I'm very sorry for this brief discussion. You can ask all of your questions in the forum or right now. I will be very glad to answer all of these and discuss it in more details. So for the conclusions, our studies has proved that there is possible suitability of this object to be used in solid-state applications. And we also observed that there are also energy transfer processes between dopant ions as well as from defects of unknown yet nature. So the further studies are required using different techniques, a wide variety of techniques. Also, there is some preliminary results that ionizing radiation can, and this should be studied too, but this is clearly out of the scope of our research, and it opens another possibility for these materials. Quick acknowledgements of all the people that have supported us in this study. Just a quick look on the slide. And that's it. Thank you for your attention. I'm ready to discuss everything that needs to be discussed. Oh, okay. Oh, what is the light yield of the studied materials? Okay, we have studied the light yield, integral light yield of all this object in comparison with the bismuth-germanic scintillator crystals. It is widely used in radiation detection, and a lot of researchers estimate light yield of their materials with this crystal. And the light yield was about 5 or 7% of light yield of bismuth-germanic. I'm only speaking about relative light yield, not quantitative. No, I cannot say that luminofores, the phosphors, are transferred on or not, because we only use powders. And what is the efficiency of conversion and quantum output? Unfortunately, we haven't studied this these characteristics, and are phosphor transparent? I have already answered this question. Anything else? Again, I'm ready to discuss it in the forum. We cannot hear you.
Спасибо, Елена. Уважаемые коллеги, еще вопросы созрели у слушателей? Пока вопросов нет, пожалуйста, на форум для обсуждения.
You're welcome to ask your questions in the forum.
Коллеги, наш докладчик из Китая все-таки имеет некоторые проблемы технические, но его помощник вкратце представит доклад.
Well, dear colleagues, our Chinese report is still handling some technical problems, but his assistant will be able to present his report.
Сейчас минуточку с доступом, да, вот мы решим вопрос.
Just a minute, we need to deal with the access issues.
Угу. Так, у меня села батарея, это самое, не заряжается.
Ну, все.
Угу. Мне просто Джуньяну надо сообщить. Угу. Угу. Джуньян, профессора Хана, ты нас слышишь?
Do you hear us?
Телефон подводит меня. Угу. Угу. Не хочет включаться. Так, ну сейчас еще минуточку мы улаживаем технические проблемы. Надеюсь, получится. Не включается. А в личных это вот здесь, да? Уважаемые коллеги, видимо, технические проблемы не удалось все-таки до конца преодолеть.
Well, dear colleagues, it seems that the technical problems remain unsolved.
Сейчас еще сделаем одну попытку.
One more attempt.
Джуньян, еще одну попытку делаем. Ждем тебя в эфире.
Junyan, we are waiting for you on air.
Go to air. Go to air. Джиньян, напиши в чате, слышишь ли ты нас?
Junyan, please write in the chat if you can hear us.
Но, видимо, Джиньян не слышит или не имеет технической возможности ответить.
It appears Junyan doesn't hear us or doesn't have any technical possibility.
В таком случае, уважаемые коллеги, работа сессии на сегодня у нас завершается.
In this case, the session is over for today.
Спасибо всем большое за участие, за ваши доклады, за интерес
Thank you
к
very much
докладам, вопросы.
for your interest in the reports and your questions.
Еще раз напоминаю, что все, что вы не успели спросить во время сессии, можно спросить на форуме и обсудить это с автором доклада.
Once again, I remind you that if you still have any questions, you can easily type them in the forum and discuss it with the author of the report.
Напоминаю, что сегодня в 13 часов по московскому времени состоится пленарная сессия.
I remind you that today at 13 Moscow time, you will have a plenary session.
Всех ждем на пленарной сессии. Будет сегодня выступать профессор Андрей Кузнецов.
We are welcoming everybody. Andrei Kuznetsov, Professor Andrei Kuznetsov, will give his speech today there.
На этом работа завершена сессии. Всем спасибо, всем всего доброго.